So, good afternoon, everyone. Welcome to the 10th lecture of this problem solving session for the structure analysis course, wherein we will try to solve the problem for the topics that you have covered in this term week. Let me share my screen first. So, this is the 10th week of this structure analysis course, wherein we have covered up to the major parts of the structure analysis course, wherein we have dealt with the problems related to the determinate as well as the indeterminate structures till now. And we have came across various problems that how we can solve them using various methods. That is, for the determinate structures, we have uh, for determinate structures, we have a method of virtual word, unit load method, conjugate beam method, moment area method. And all of these we have together incorporated in our analysis to determine the deflection that could be either horizontal deflection or vertical deflection, and various slopes at different points of the beam section or the truss member or any a frame member. So, my name is Pranav Mahajan. I am your PMRF scholar for IIT Madras in Department of Civil Engineering in Structural Engineering Division. So, till now, what we have covered, so up to week 9, we have covered the analysis of structure determinate statically determinate structures, as well as few parts of indeterminate structure, wherein we have looked the problem for the problems related to trusses as well as beams. So from the starting week, we have started with the equilibrium equations, wherein we have seen that how we can utilize various problems related to determination of reaction forces as well as the shear force and bending moment at different points along the beam section. Then we have moved to the truss, in which we have seen that truss is a two-force member, and in which compression and tension are the major forces that come into the picture. So to determine the unknown forces in the truss member, we have used two methods. One is method of joint and another is method of sections. So after that, we have moved to the V3, wherein we have seen that how to determine the deflection of the trusses using principle of virtual work and unit load method, wherein if you apply a unit load at a particular direction, it will give you the value of deflection at that particular joint. Then we have also utilized the concept of moment area method, conjugate beam method to determine the deflection of beams and frames. Then for moving loads, we have considered influence line diagram based upon Mueller-Breslau principle, that how can it be incorporated to determine the reactions, moments, shear along the different at different points along the length of the span of the bridge on which the this moving load is moving throughout its length, or the truss member, and in which how the compression forces and tension forces are developed, and what kind of reaction forces are developed, and based upon that we can design the structure depending upon the amount of loading that is moving over the structure. Then we have, by this, we have completed our analysis of statically determinate structure. Then we have moved to the statically indeterminate structure, wherein we started with the introduction of force method, in which in force method we are utilizing the concept to determine the unknown displacements in the structure, whereas in stiffness method we are using the concept to determine the unknown forces that are there in the structure. So using that, we have started with the method of consistent deformation in trusses, in which we have utilized the concept of flexibility matrix and applied them to determine the unknown reaction. So in this, redundant forces are the major concerns that come into picture. So first of all, we will remove the redundancy from the so starting from the first we will calculate what is the degree of static indeterminacy. So after determining the degree of static indeterminacy, to determine whether which component should be taken as redundant. So, depending upon the type of the problem, the redundancy may also differ from problem to problem. So, we will remove the redundant members and make the structure to be determinate. After making the structure to be determinate, we calculate the forces and draw the reaction, shear force as well as the bending moment diagram for the structure. Then we have utilized the concept of uh, removing, adding the redundant force, and then trying to analyze the problem. So based upon that, we have calculated uh, the redundant forces that are there in the member, and after that redundant forces are calculated, now the structure is determinate, and then based upon the equilibrium equation, rest of the unknown reactions as well as the moment that are there in the structure can be calculated. Then in the previous last week, we have seen the utilization of three moment theorem in continuous beam. So in continuous beam, if you have a large number of spans in the structure, you can utilize the concept of three moment theorem to determine the moments at different points of the continuous section. So what we will cover in this current week is to determine the slope, is to use the slope deflection method and determine the moment at the ends of the beam element. Okay. So what is slope deflection method? So slope deflection method gives you a relationship between slope, deflection, and bending moment. So it will give you a relationship between slope, deflection, and bending moment. That means how the bending moment is related to the slope and how the corresponding slope is related to the deflection. So this is what we will calculate from the slope deflection method. So by forming slope deflection equation and applying joint and shear equilibrium condition. That means if we take the slope deflection equation and also apply consistency equation. What do you mean by consistency equation? That if you have calculated the slope deflection equation and from that you have calculated the moment equation and you consider a joint at any particular point, and at that particular joint the total moment is zero. So that condition will be your consistency equation for that particular joint. So by forming the slope deflection equations and applying the joint and shear equilibrium equations, the rotation angles or the slope angles, that means the slope that is there in the structures are calculated. So after calculating this rotation angles or the slope, we will substitute them back into the slope deflection equation, and then member and moments and are radially determined. So if we have the value of theta available with us, we will utilize them in slope deflection equation, and using that we will calculate the end moments of that particular span. So deformation of the member is due to the bending moment. That is why we are using this slope deflection method to determine the bending moment. When a simple beam of length LAB and flexural rigidity EI is loaded at each end with clockwise moment MAB and MBA. Okay, so then the member end rotations will occur in the same direction. So these rotation angles then can be calculated using the unit force or the Darcy law. So how we can determine that theta angles? So theta angles are calculated like this. So these are the two equations that will help us to determine the angle of theta. And we have seen these equations in previous week for the three moment theorem, and we have utilized them, we have derived them and determined the and finally after using them only we have calculated the equation for the three moment theorem. Okay, so these equations are the basis for for deriving the slope deflection equations for a particular span. So now after deriving the slope deflection equations, we will see how the problems related to them can be easily solved. Okay. So talking about what we have covered till now, so we have covered force methods as well as in coming week we will cover displacement methods also. So which method come under which, that is either it comes in displacement method or in force method, we should know. That is, first we have seen the virtual word method. It comes under force method because forces are available with us, and or not available with us, we will calculate the forces, and then based upon the forces we will calculate the displacement in the member. Same thing we have utilized in method of consistent deformations also, in which we will try to determine first the redundant force, and based upon the redundant force we will make the structure to be determinate, and then calculate the uh, remaining remaining reactions or moments using equilibrium equations. Then comes three moment theorem. So in three moment theorem, you directly apply into that particular uh, equation, and that is also based upon some conjugate beam method, in which you will draw the further bending moment diagram for that particular span, and you will calculate the area and corresponding uh, centroid of that particular bending moment diagram, and that will help you to determine the moment at different points of the beam. Then Castigliano theorem also we have utilized. We are also utilizing this force method for Maxwell-Moore equation. Then same thing we are utilizing for column analogy method, where we use this displacement method. So displacement method we use uh, in moment distribution method. In next week we will see some for problems related to moment distribution method. Then Carney's method, slope deflection method, that we will cover in this week. So yeah, so it will come in the displacement method. So what do you mean by that? It means that by based upon the forces that is available with you, you will calculate the displacements. Okay. Then first moment, Castigliano first theorem is also based upon displacement method, and finally the stiffness matrix method. Okay, so these are the few methods that you can distinguish between force as well as the displacement method. So force and the displacement method are the broad categories in which different method that you will see are come under different categories. So it will help you to understand that which method comes uh, uh, under whether force method or displacement method, and it will help you to clear your concepts. So let's start with some questions related to that. So first question is, if you have a propped support end. So let me read the question first. So if the propped support end of a propped cantilever beam of length L and constant EI settles by delta, then what will be the moment in the fixed end? Okay, so let me draw the beam first, then it will be easy for you to understand. So it means that you have a prop cantilever. So for this is your cantilever beam, and it is propped at its free end. Okay, so this end is propped. Yeah, so this end is propped, and this whole length is L, and it has a constant EI. That is EI here is constant. And in this, it is mentioned that the support settles by delta. So if the support settles by delta, so the beam will look like this. Okay. So this is your delta. Okay. Now it is asking you to determine what will be the moment at the fixed end. So based upon as the corresponding support has settled by delta, so we have to calculate what will be the moment generated due to the settlement. Okay, so if the beam is settled, so it will develop some moment that will be, yeah. So this moment will be 6 EI upon L square. Let me 6 EI delta upon L square. So it will be 6 EI delta upon L square. So this moment will be acting over the member due to the settlement of support. So now since the support has settled, so but to make but this is a propped support. In this, external moment cannot be there. So to counteract that, and clockwise moment is required to be applied. So if we apply clockwise moment, let me make it with a different color. If we apply clockwise moment to make it in such a way that the moment at the propped end should be equal to zero. So here this will be 6 EI delta upon L square, and it is in clockwise direction. And based upon that, what will be the moment that will be developed here? So in this, the anti-clockwise will be, so here carryover moment will be half of the moment that is developed in the support. It will be 3 EI delta upon L square. Okay. So this moment is applied as there is there will be no moment at the propped support. That's why we have applied this moment at the propped end. Okay, because due to settlement, the 6 EI delta upon L square will come into picture. So to make this propped system to be having zero bending or zero movement at that particular support, will apply a moment of same amount but in counter direction, that is clockwise direction. So based upon that, uh, this is the carryover moment. So this is the transferred or distributed moment. Okay, so if the if the support settles, so this moment is generated. So if this 6 EI delta upon L square is generated, so to make the structure to be stable, the carryover moment is applied at the fixed end support. That will be 3 EI by delta square. So your moment at fixed end due to settlement will be equal to 3EI delta upon L square. Okay. So now let's move to the next question. In this question, it is provided to you that the support B of the fall. Let me read it first, and then I will explain the meaning of that. So in this, the support B of the following beam undergoes downward settlement of 10 mm. The slope at the support B, no, calculate the support at the support, calculate the slope at the support B for fixed end moment. Clockwise moment is taken as positive, given EI is equal to 100 kilonewton per meter square. So since the support has settled and it is a hinged support at A, so it will be, so deflection shape will be like this after settlement. So by this amount, since it has settled, let me change here also, because here it is not from, okay, fine. So here the settlement is this much. So this is your delta. I will write the delta to be equal to 10 mm as given in the question. We have EI also here equal to 100 kilonewton per meter square. So you have to calculate theta B due to the settlement. Okay. In this, it is mentioned that we have to take the clockwise moment to be positive for the fixed end moment. So how it will come into picture, we'll see using the concept of slope deflection equation. Okay. So let's write. So for the first beam, that is for beam AB, MAB is given by MAB, that is fixed, okay, plus 4EI upon L, or I will directly write it as 2EI by L. That will be easy for you to understand. Not 2, directly EI by L. So MAB EI upon L twice of theta A plus theta B, and some deflection is also ordered. So that will be 3 delta by L. Okay. So what will be your final equation? That will be here moment, since there is no load at top and bottom, because fixed end moment will only come into picture when external load is applied. So I will write here also fixed end moment will come when external load is applied over the structure. Okay. So in this case, your MAB will be equal to 0 plus, since MAB here is equal to 0 and slope, since it is a fixed end, so here theta A will also be equal to 0. So your first term will be equal to 0. Now your next term is 2 upon 2EI theta B. What is the value of L? L here is 5. Okay. And then your next value will be 6EI delta upon L square. So L square is 5 square 25. So your final equation will become 2 upon 5 EI theta B minus 6 EI delta upon 25. Similarly, we will derive the equation for span for BA also. So your MBA will be equal to MBAF plus 2EI upon L. Now theta B will be twice. So if you only want to remember that, so then just see whichever moment you are writing, that is MBA you are writing. So the first letter will be the twice and the second letter will be come only once. So twice of theta B plus theta A minus 3 delta upon L. Okay. In this case also, your MBA is equal to 0 for the fifth support. Here theta B will come into picture, so it will be 4EI theta B upon L. So L here is 5. So theta A again will be equal to 0 and delta will come into picture. So it is 6EI delta upon L square. So your next final equation will be 6EI, oh sorry, 4 by 5 EI theta B minus 6EI delta by L square. Now you have another additional span also, that is BC. Your BC is overhand structure. Okay, but in this case also your MBCF will be equal to 0. Okay, so using the equation, you have, since the total moment at B, so MBA plus MBC should be equal to 0. MBC, since this is already equal to 0, so your MBA will then become equal to 0, and based upon that you can calculate the value of slope at that point B. Okay, so you have from MBA 4 by 5 EI theta B minus 6 EI delta upon L square equal to 0. So I will write the L square also as some value that is there. So your L square here is 25. Okay, so 25, 25, and top one also it will be 25. Okay, so now substitute all the parameters that is given to you. Let's reduce the equation first. 4 by 5 theta B minus 6 delta upon 25 equal to 0. And if you make it more simpler, that will be equal to theta B is equal to 6 delta upon 25 into 5 by 4. So you have the value of delta here as 0.01 radians, not 0.01. It is like you will write in meters because everything here is in meter. So that will be equal to 6 into 0.01 divided by 5 into 4, 20. Okay, so your value here will come out to be 0.003 and it will be in radians. Okay, so this is your answer for theta B. Now, using these same concept, we will try to solve different problems in the coming questions. So now in the same question, if you are required to calculate the absolute moment at the support A, then how you will calculate? Okay, because earlier you don't have the value of theta B, now you have the value of theta B. Then how you will solve? So we will write the MAB equation first. MAB, what is the value of MAB? MAB here is 2 by 5 EI theta B minus 2 by 5 EI theta B minus 6 upon 25 EI into delta. Okay. So now we will calculate the absolute value. Substitute theta, delta, and EI. So we will take EI outside, take 2 by 5 into theta B. Theta B comes out in the previous question as 0.003 minus 6.25 into delta. Delta we have calculated, we have seen the question as 0.01. So solving that, we got the value equal to minus 1.2 into 10 power minus 3 into EI. And this will give us the value equal to, because multiplied by, so EI is 100, so it will give you value equal to 0.12 kilonewton meter. So your MAB is 0.12 kilonewton meter. Yeah. Now let's solve another question. So this is your continuous beam in which one span is loaded with uniformly varying load of 48 kilonewton per meter, and you have a concentrated point load of 80 kilonewton in between B and C, and it is not at the middle point, it is at a distance of 3 meter from support B. So what is required in the question? So in question it is mentioned, choose the correct slope deflection equation for member AB to for the following given beam under given load conditions. For fixed end moments, clockwise moment is taken as positive, EI is constant. So we have to write only the slope deflection equations. So first of all, we will write, since the loading is given to us, we will write the fixed end condition for the span AB as well as for span BC. So fixed end moments. So what are the fixed end moment here? So you have MABF, that will be equal to minus WL square upon 30, and MBAF will be equal to positive WL square upon 20. Fine. So substitute the values. What you will get? You will get minus 48 into 16 divided by 30, and this will be equal to 48 into 16 divided by 20. So by this you will get the value as minus 25.6 kilonewton meter, and this value is equal to 38.4 kilonewton meter. Okay. So next is MBCF, that will be equal to minus PAB square upon L square, and this is MCBF. We can write it as minus P. In this case, it will be A square B upon L square. Fine. So this moment will be positive. So minus P is 80. 80 into 3 into 1 plus square is 1, divided by L square. 4 square is 16. And then 80 into 3 square is 9 into 1 divided by L square. L square is 16. So you will get the value as minus 15 kilonewton meter, and this will be equal to 45 kilonewton meter. Now you have calculated all the slow fits and moments. Now we can directly apply now using slope deflection equations. Our MAB will be equal to, so what value we have dot? First value we have dot as minus 25.6 plus 2EI upon L. L here is 4 meter, twice of theta A plus theta B. Okay. In this case, since the support A is fixed, so your theta A will be 0. So this term will be gone. So the only term remaining with you is theta B. So that will be minus 25.6. Put the value of EI. So EI is given here is constant. So that will be your zero point 0.5 EI theta B. So this is your equation for MAB. Now MBA, in this case your fixed end moment is 38.4 plus 2EI upon L into twice of theta B plus theta A. That will be, in this case also your theta A will be equal to 0. So what you will get? You will get 38.4 plus EI into theta B. Now what will be the third equation? MBC. So what will be your MBC? In this case, your first term is negative. So negative 15 will come into picture plus 2EI. Total length here is also 4. Twice of theta B plus theta C. That will be equal to, since both are there, so it will be minus 15 EI theta B plus 0.5 EI into theta C. Right? Now the fourth equation that is remaining is MCB. That will be 45 plus 2EI upon L. L is 4 plus twice of theta C plus theta B. That will be equal to 45 EI theta C plus 0.5 EI theta B. So all the four slope deflection equations now we have determined. Now apply the consistency equation that I have already told you. So in this case, at support B, since there will be no moment, so at that point, using consistency equation or compatibility equation, your MBA plus MBC will be equal to 0. Okay, so let's write the equations. So for MBA, what you have written? You have written it as 38.4 plus EI theta B, and for BC it is minus 15 plus EI theta B plus zero point 0.5 EI theta C. That is equal to 0. So it will give you twice of EI theta B plus zero point 0.5 EI theta C plus 23.4 equal to 0. This is the first equation, and another equation is MCB is equal to 0, because at ends there will be no moment. So that will be your 45 plus EI theta C plus zero point 0.5 EI theta B equal to 0. Now say, take this as your equation 1, and this will be your equation 2. So we will solve both of them equations, and we'll try to get the value of theta and theta c. Two equations, two unknown. Now we can easily get. So solving 1 and 2, we get EI theta b is equal to minus 18 upon 35, and that is equal to minus 0.51, whereas EI theta c is equal to minus 44.74. Okay, so these are the things that we are required to be calculated. So what is mentioned here is, I think in this question we are only required to calculate up to this part, bending moment equation. I have tried to solve further also. Let me remove from here. I think we will solve, use this in next question. So I will cut it from here. Yeah. So here we require that. So I'm pasting it here. Right. So in this question, you are what? So this is the end of the question number 4, in which you are required to calculate only the slope deflection equations. So in the next question, it is mentioned, using the slope deflection equation of member BC, then equilibrium equation at B is determined. Then determine the equilibrium equation at the point B. Okay. So you have to utilize the equilibrium equation at point B and then solve the problem. Okay, that you have done. Now, in the next question, you are required to calculate the absolute value of beam, absolute value of moment at support A and B. So how you will do that? So your MAB is equal to minus 25.6 plus 0.5 EI theta B. So substitute the value of EI theta B. What you will get? You will get minus 25.6 plus zero point 0.5. What is the value of EI theta B? So EI theta B, you have calculated it as minus 0.51. So you will get MAB equal to minus 25.855 kilonewton meter. For MBA, the equation is 38.4 pi theta b. So it will be 38.4 minus 0.51. It will be 37.89 kilonewton meter. Now for MBC, your equation is minus 15 EI theta B plus zero point 0.5 EI theta C, and it is equal to minus 15. What is the value of EI theta B? It is minus 0.51, and plus zero point 0.5 EI theta C is minus 44.74. Okay, so solving that, you will get the value as minus 37.89 kilonewton meter. And same MCB, as we have already written, as it will be equal to 0. So now you have all the moments. We can all even draw the bending moment diagram for this current continuous beam. Okay, so this is how we will solve the problems related to beams using slope deflection method. So we have the next question available with us. In this, we are given a portal frame and we are required to calculate the unknown forces that are there. So consider the portal frame under given load to determine the unknown forces. For fixed end moment, clockwise moment is taken as positive, and what will be the correct absolute value of slope at theta at b. So that means you are required to calculate theta b. So how you will do that? So first we will calculate the value of this UDL that is given to us. So it is, so bending moment here will be WL square upon 12 at ends. It will be 24 into 3 square is 9 divided by 12, and that will be equal to 18 kilonewton meter. Okay, so fixed bend moment we have calculated. Now start for beam AB. So MAB is equal to MABF plus 2EI upon L into twice of theta A plus theta B. So in this case, your MABF is equal to 0, theta A is also equal to 0, and you will be only remaining with theta B. Okay, so what is the value here? So that will be equal to 2EI theta B upon 5. Sorry, in this case it is 2EI now. So take anything to be 2. So suppose I am taking I equal to 2. So here 2 also will come into picture. 2 into 2 into, and this whole value will be, so this will be equal to 4 upon 5 EI theta B. Similarly, calculate for MBA also. So your MBA will be equal to MBAF plus 2 into 2EI upon L twice of theta B plus theta A. In this case, why I have added additional 2 is because you have given EI as 2EI. So here also BA will be equal to 0, theta A will be equal to 0, and you will be only left with 2, 4 into 8. 8 upon 5 EI theta B. So that will be equal to 1.6 EI theta B. Okay. First value you have calculated. Now next value is you are required to calculate MBC. So MBC is simple beam with a uh, overhang of 1 meter. So that will be equal to, since it is provided horizontal moment, so it will be equal to minus 6 into 1 equal to 6 minus 6 kilonewton meter. Next thing that will be MBD, and that will be equal to MBD MBD F plus 2 into, since here it is EI only, so no double will occur, 2 EI upon L twice of theta B plus theta D. Okay, so this will be, since it is WL square upon 12 in negative, so we have calculated value as minus 18, so it will be minus 18 plus 4 upon what is the value, 3 EI theta B, and theta D here will be fixed, so that will be equal to 0. So now, using compatibility equation, the moment at the point support B at point B is equal to 0. So that means your MBA plus MBC plus MBD will be equal to 0. And you have only one unknown here, that is theta B, that can be calculated. So what you have calculated here is 6 EI 1.6, sorry, EI theta B. BC is minus 6, then it is minus 18 plus 4 by 3 EI theta B equal to 0. So that means 44 upon 15 EI theta B is equal to 24. Okay, so from this you get EI theta B equal to 90 upon 11, and it will be equal to 8.18. So this is what is asked in the question. You are required to calculate the slope. So if you want to write in terms of slope, so your theta B will be equal to 8.18 divided by EI. Yeah. So this is what is asked in this question. Now in next part, what is asked? So it is asked that you are required to determine the absolute bending moment at support D. At D, we are required to calculate the bending moment diagram. Sorry, bending moment. So we have not even write the equation for D. So first write the equation for support D. So your MdB will be equal to MdBF plus 2 EI upon L twice of theta D plus theta B. Okay. So in this case, your MdB is WL square upon 12, and that value is equal to 18 plus 2 upon 3. Sorry, we will write directly as 4 upon 3. 4 upon 3 EI theta D plus 2 upon 3 EI theta B. So in this case, we already know that theta D is equal to 0. So this will become equal to 0. So here MD will be equal to 18 plus 2 by 3. What is the value of EI theta B you got here? We got it as 8.18. It is 8.18 equal to, so you got the value as 23.45 kilonewton meter. Okay, so you have got the value. So if you are required to calculate, determine the bending moment diagram, that also you can do. You have the equation for AB also. Substitute the value of EI theta B in that, and then you will get to know the value of MAB. MBA you already know. Then M theta, BD and DB you have calculated. So based upon that, for any frame, that is whether it is a continuous beam or it is a continuous beam or it is a portal frame, you can determine the bending moment diagram using slope deflection method. Okay, so this is what we have covered in this week. So in this week, how we have started. So we have started with, let me open the slides first. Yeah. So we have started with slope deflection method, in which we told that it is a displacement method. So this is a displacement method, and it provides the relationship between bending moment, slope, and deflection. Okay, so based upon the equations that we derive for theta b and theta c, or any thetas that are there unknowns in the beam, based upon that we can calculate the end moment of that particular beam or portal frame element. So we told that there are different elements that is available for force method as well as for displacement method. For force method, it can be calculated using virtual work method of consistent deformation, three moment theorem. That you, some method of some method that are listed here you have already covered. And for the displacement method, you will cover the MDM as well as Tani method in the coming week. Okay, so starting with the questions we have came across when there is a support settlement. So moment of 6 EI delta upon L square will come into picture. And for the carryover moment, it will be half of that. So it will be 3 EI delta upon L square. Okay, so for next question, we have utilized the concept of slope deflection equation. And when there is slope settlement, there sits EI upon delta upon L square will be added up, and we will solve that and determine the value of different span, that is MAB, MBA, then MBBC. And to determine the unknown, that is theta B, that is there, we will apply equilibrium equation or the compatibility equation at the particular joint where the moment should be equal to 0. So in this case, it is theta B. Sorry, it is support B. So at B, if we take MBA and MBC equal to 0, we can get to know the value of theta B. Same thing we have applied in next question, and then we have determined the first the fixed end moments, and then after determining the fixed end moments, we have derived the different moments that are there in the structure, that is MBA, MBC, MCB. After that, we have utilized the compatibility equation and determined the value of EI theta B and EI theta C. Okay, and then in after calculating EI theta B and theta C, we have got to know the value of support at moments at supports. that is MAB, MBA, MBC, and MBCB. Then we have determined for the portal frame. So you have loading in portal frame, how you determine the and moments as well as the slopes at different points that we have seen in this. So in this week we have tried to cover the problems related to slope deflection method, and what we will see in the coming week is that, so since week 10 is completed, only 2 weeks are remaining. So in the coming week, you will see the moment distribution method as well as the direct stiffness method for the problems related to indeterminate structures. So by this, I will end this session. Hope you have liked this session. If you have any query, you can post in student discussion forum in Swayam app. We will try to resolve your query as early as possible. So try to solve the problems related to slope deflection method and get to know about your queries. So by this, I will end this session. Hope you have liked this session. Have a nice day. Enjoy your weekend.